Okay, well, thank you for being here. It's always slightly daunting talking on education things with people like Cecilia in the room, so I'll just ignore the fact that she's here and talk to the rest of you. So, this is basically what I'm going to do today, as Hanley suggested. I'm basically going to frame first what legitimation code theory is and what the problem is that Carl Maitland is trying to solve in terms of producing this theory, and then look at how I've chosen to apply that in the teaching of chemistry. The detail, a lot of the detail of how I've actually done that is in the paper. So if that seems a bit confusing, you can look at that later or ask me questions. Okay, my presenter's not working, never mind. Okay, so basically this comes as a response to the question of knowledge and education. If you've been following any of the higher education literature in the last couple of decades, there is this strong move, and a lot of the not only the higher education literature, but a lot of the literature that comes through government documents. The focus is on the new knowledge economy. This is where we are supposedly at the moment. So a lot of the focus then is on knowledge and the production of knowledge and the dissemination of knowledge. But there's a major gap in the middle of that. This is a quote from Carl Maitland's book Knowledge and Knows, right in the introduction. A quote from Daniel Bell actually saying, knowledge is a set of organized statements of facts or ideas presenting a reasoned judgment or an experimental result which is transmitted to other through some communication medium in some systematic form. Thus, knowledge is distinguished from news or entertainment. And I don't think any of us would find this a particularly problematic view of knowledge. The difficulty comes in looking at what knowledge actually is. As soon as we begin to drill down a little bit deeper into, we all presume that we know what we're talking about when we're talking about knowledge. And as soon as we begin to drill down into that, it all gets a little bit murky. And as soon as we start trying to talk cross-disciplinary terms, it becomes even more tricky. So again, just a quote from, just looking at, of course, what about differences within knowledge? Of course, Andre Brink has been in the news, not so much for the last month or so, but this slideshow I first put together for a talk that I gave at UCT, just after Andre Brink had died. Obviously, there's a difference between the kind of knowledge that we interact with when we're reading a dry white season versus looking at the hunt for the Higgs boson, which is full-on hectic physics that I struggle to understand. So knowledge is thus one of the most discussed and one of the least discussed issues in the academic debate, in that knowledge is everything to society, but he says is nothing to social science. So we talk about knowledge a lot, but we don't discuss terribly much how knowledge is created and how knowledge is then passed on, and what it is that we're doing in an educational environment. One of the questions that I think is an interesting one, and this is particularly an interesting one for me as a chemist, is this idea here. One of the organizing principles of knowledge shape the spatial and temporal reach, the modes of engagement and forms of development of social fields. They are key to social inclusion and social justice in both education and civic life. Though made by us, knowledge possesses properties and tendencies of which we may be unaware, and which may lead to consequences that are unintended, even contrary to our own beliefs. Obviously, coming from chemistry, I imagine that most people, I haven't actually tested this out, but most people within chemistry will think that knowledge is a fairly neutral thing. That there's no, the kind of the social implications implied by this kind of view of knowledge is not even really thought about in much detail in terms of chemistry education. So one of the things that's interested me in, and one of the things that kind of hooked me on legitimation code theory, was beginning to, it gave me firstly a frame for beginning to understand some of the problems that people are talking about in the higher education literature, which we don't even think of as being issues in chemistry. Slightly embarrassing, but that's the truth of it. So it opened up for me the space in which the debates that were going on in the higher education community at the time that I got interested in education research. This broke open that for me in a particular way, and because he uses graphs and things, I'm a good scientist, and that attracted me. But also, I think more importantly, it's designed as a set of tools that can be used in any educational enterprise to critique any aspect of the educational enterprise that you're involved in. And I think that then gives us a way of beginning to communicate cross disciplines where we're using the same higher order language to talk about the problems that we have. So it gives a way of communicating across disciplines that I think sometimes fails with some of the things that are more particularly focused on sort of the social science disciplines. I'm happy for people to argue on that point. It just seems to me that it's a useful one. So legitimation code theory then is a conceptual framework which affords the interrogation of knowledge practices. And certainly in the probably late 1990s, early 2000s, or certainly into the mid-2000s, education research had become very focused on learning. And in a sense, legitimation code theory emerges as a response to that actually there's more to education than simply learning. The knowledge that we're dealing with is also worth investigation. So again, that's the angle that he's coming from, and pulls it up against this false dichotomy which existed in the literature at the time, and is still quite prevalent, I think, in some of the less highly theorized scientific education literature, that there's this false dichotomy between what he calls the constructivist relativism and positivist absolutism. That there's the everything, we create knowledge versus knowledge is something that exists out there. That actually that's a false dichotomy. And it's more complex than that. So, legitimation code theory, that's just a weird term, right? What on earth is that about? Well, basically the idea is that it's critiquing what makes knowledge legitimate. So that's the legitimation part. The code part comes in that there are a bunch of different codes. There are a few more codes now, but the literature isn't out yet on them. So these are the ones that exist so far. I'm just going to discuss two of them today, the specialization code and the semantic code, mostly because I still have yet to figure out how the others apply to chemistry. I haven't got my head around that yet. I know that it should, but I haven't got my head around how yet. So the first one, and certainly the one that I find easiest to get my head around in terms of an introduction to legitimation code theory, is the specialization code. And essentially what that's looking at, I'll show you a graph in a minute, is the dynamic between epistemic relationships and social relationships. And as I said a little bit earlier, whoever controls the device establishes what knowledge is legitimate. So there's definitely a power relationship that exists within this. How does that work in terms of the specialization code? Well, this is the specialization code here, and this is the classic sort of making diagram where you have those of you who know Some of Bernstein's work will recognize a similar kind of dynamic that exists in his work as well. That you have these two axes. The social relations, basically looking at how important the person of the knower is, if I can put it that way. I'll explain what I mean in a minute. And the epistemic relations is essentially looking at the strength of the knowledge itself. So, or the definition around that. There are four codes that obviously you can sit in any of these four quadrants. If we take science, which is obviously the place where I sit, the epistemic relation is very strong. There's a very clear sense of what, nobody's really confused apart from at the boundaries about what is legitimate chemistry. I mean, obviously once you start drilling down, of course there are questions around that, but it's quite clear what that's about and what it takes to produce what good solid chemistry looks like. There's not much dispute around that. In terms of the person of the chemist, it doesn't really matter what background you come from. If you can learn how to do chemistry, you can produce good chemistry. Nobody's going to worry, as it happens, one of my colleagues has dyed her hair blue. It's okay. Nobody questions her ability to be a chemist because she has blue hair. This is the kind of the issue around the social relationships. What it takes to present yourself as a good chemist is far less important than your capacity to produce something that looks like chemistry. At the opposite of that would be far more the humanities. We now have a major dispute over what legitimate work looks like in that field. So the person who's producing it becomes much more important, and what that person looks like. Not necessarily physically looks like, but the package of that person becomes significantly more important. That you have to have learnt and embedded yourself in the acceptable discourse of that field. There's less about the knowledge and more about how you present it. The elite code then would be something like music, where both things matter. It is exceptionally technical, and it matters that it looks right. The relativist code, the example given in, I think, Knowledge and Knows is history. I really can't comment on that. I'm not even gonna go into a discussion on that. But I think it gives you some sense of, again, if you look at where Macon's coming from and the idea that knowledge and how we package it has social implications, this then becomes very important in terms of who's coming through the system and who can produce. And our educative project of how do we take someone from a very different social background and make them eligible to be an expert in whichever particular field. So again, I find it a useful way to begin to get into his thinking, but again, in chemistry, this is not a conversation that even happens. So, what I have used in chemistry and what I've found useful in chemistry is the semantic code. Semantics, of course, is to do with meaning. And he divides these into two different axes, semantic gravity and semantic density. The easiest way to think about this is that if you go from, if you move across towards greater semantic density, you're moving towards greater complexity in terms of the representation. I'll give an example in a minute of exactly what this means in chemical terms. But it's kind of the use of jargon or the use of symbols or that the appropriate use of technical words is the movement from left to right. The movement upwards is a move from the real world into the abstract. Another way, which isn't technically correct, but you can think of it as kind of looking also from the more specific to the more general case. There's a weird complexity here in that he talks about this being lower semantic gravity. It's the one thing where he switches. Just don't worry about that, I'm just pointing it out right now. Yeah, yeah. That's exactly why he does it, but it gets very confusing when you're talking about increase and decrease and.
That's the only reason you chose it, isn't it?
Absolutely, it was to confuse the audience. That was my reason. So, how does that work? Sorry, I keep forgetting this isn't working. In chemistry, this is sodium chloride dissolving in water. This would be the simplest version. This is the real world example, right? You can do this in the lecture theatre, provided you don't spill stuff. Very simple, but there's absolutely no chemical information in this example here. So the increasing abstraction, becoming more abstract, is to describe, using words that the students will understand, what is going on in terms of what they see in that glass. So it's beginning to move into the abstract, which is what is actually happening on a chemical level. Moves us up into this quadrant here. The move into semantic density is to use a symbolic representation for what is happening in the glass. And basically what's happening, the green is the chlorine, the white is the sodium, and the red and white are the water molecules, and they're happily dissolving. Now, why is this important? Because as a chemist, I could write probably certainly 1, if not 2 pages on what this little equation means. The first year sitting in the class is going, NaCl, what's that again? Forgetting that the state symbols are important, what does the arrow mean? A whole bunch of things gets incorporated into this equation. Now, what I've done with that then, I'll give another chemical example in a minute. But thinking about things in this way, I began to realize that one of the things that we do in chemistry, in fact, let me give the next example. Sorry, it's a very technical chemical example. But basically, in second year organic chemistry, we talk about something called the Grignard reaction. And we happily expect, once I've explained it once or written up this equation once, we expect our students to know what we mean when we say Grignard reagent. Forgetting, of course, that they may not recognize that you pronounce this as Grignard. There's that complexity too. But there's a whole bunch of information that goes into something like a named reaction, which we fail to recognize that the students don't necessarily get. We happily move, I think most of organic chemistry teaching will sit in this quadrant over here. We'll talk like this and we'll use these symbols, but we'll forget that the students are actually still trying to remember what an alkyl halide is. So the movement between the different quadrants in terms of teaching becomes very important. To move explicitly forwards and backwards in this direction, so to make sure that you've got the symbols and are using the appropriate simpler words with the symbols, and moving back again, giving the symbols and asking the students perhaps for for the words to describe them. And crucially, and I think this is the step that we miss out on in chemistry, is the move to lower semantic gravity. We spend almost all of our time, and examining a bunch of different tests and exams, we spend most of our time in the bottom half of the graph, and presume, because we're in the bottom half of the graph, that the students are actually with us up here. So it gives a way of one, in terms of teaching, beginning to talk using the semantic gravity and semantic density, and moving between low semantic gravity and high semantic gravity, and low semantic density and high semantic density, to make sure that the students are actually incorporating that knowledge. That's what Making will call the semantic waves, is making sure you're not simply going from abstract to real world, and abstract to real world, and abstract to real world, but you're also going from real world to abstract. You're moving in both directions. Most of us naturally, when we teach, will use one direction or the other, and the importance of actually moving in both directions. Secondly, and crucially, it's given me a very useful way of critiquing the tests and exams that I produce. Obviously, it's much easier to critique other people's tests and exams. So I started doing it by doing that, obviously not explaining that to other people, but doing that with some of the exams that I was being asked to look at. And recognizing that the gap that we have in terms of chemistry, and I think that this is part of the study that I'm doing at the moment. One of the things that we find is a major problem in chemistry is that students come through the kind of first year chemistry, and by the time they get to second year organic chemistry, they've forgotten everything that they've done. And I think part of that is because we're sitting on the lower level. They haven't actually moved into the abstraction of the process. They haven't actually made that connection. So they've lost the terminology, and because they never had the understanding in the first place, there's nothing there. We presume, because they can use the right term, that they have the level of understanding, and it's simply not the case. So that's pretty much what I have to say. I think the crucial thing here, in terms of kind of continuing the discussion, has got to be to say, what would this look like for some of the things that you're teaching? Where would those what would sit in the 4 different quadrants? It's not an easy question to answer, and it took me quite a long time to work with it to figure out where those things actually sat. But having done it, I'm finding it actually tremendously useful, and it is impacting my teaching, because I spent almost no time sitting in this quadrant here in terms of the way that I taught. Whether that'll have any impact on the students, who knows? But I think it can't harm the process of teaching. It might just help, but it's not going to harm it. And that's, the floor is open for confusion.
Confusion at all, I think. Thank you so much. I wasn't able to listen, but I'm sure it was exciting, as exciting for you to hear as it was for me. I will open the floor now. Any questions? Yes, we've got something back.
Thank you very much. That was very interesting. And well done for applying it to chemistry. I have a question on that last one.